Welcome to the ASR 1000 architecture overview and the use case presentation. We're at an exciting time as we're refreshing our product to the next generation hardware, and we're integrating to the Cisco SD-WAN architecture with the new XE SD-WAN software. The challenge is that the next generation hardware and the software require you to keep up to date on the platform innovations. That's the reason why you're here, right? Otherwise, you could miss out the great opportunities. We bring in the new hardware and the software along with the new solution we're bringing into the market. So in this session, we're going to have a good architecture view how the ASR 1000 system is built, what is really new. Then we're also going to talk about some of the new solutions and applications you can deploy the ASR 1000. So during the session, I want you to think about how you can apply the next generation hardware and the software in your upcoming network refresh or expansion opportunities, and how to leverage the new solutions to solve your business and IT problems. So by the end of the session, you will know well how the ASR 1000 is put together and how we are aligning with a software-defined networking and also with the overall Cisco digital network architecture. My name is Jason Young. A little bit about me. I am a Canadian. I came from Ottawa, Canada. So I've been working in Cisco for more than 18 years. I started as an engineer to develop a number of Cisco routing products. I don't know if you ever remember, there was a router called the GSR, Cisco 12,000 routers. That was my first product. Then I worked on Cisco 10720, which was the first router introduced the DPT, the Dynamic Packet Transport Ring technology. Then Cisco 10,000, which was a very popular broadband aggregation and a service provider PE box. Then around about 2008, I joined the product marketing organization as a TME when the ASR 1000 was FCS, so the first customer shipped. So ASR 1K is kind of like my baby. I kind of look at how it grows over the years and drive the product innovation and develop new solutions in both enterprise and in the service provider segment. So agenda, we're first going to introduce ASR 1K to make sure everyone have the same level set, what the ASR 1K is. Then we talk about the system architecture. Then we talk about the software architecture, what are the new innovations we're bringing into the iOS XE software release. Then we bring back home by talking about applications and the solutions that you can actually use the ASR 1K. This is not a configuration level session or anything like that. So if you expect a configuration or operation type of discussion, come to see me afterward. I'm happy to have a one-on-one discussion with you. And stop me anytime if you have questions. Okay, this session is not about finishing 50 slides. It's about addressing your concern, what you care about. So this is the overview of the ASR 1000 current product family. We have a fixed chassis. We have a modular chassis. They are running iOS XE as the operating systems. They're compact, powerful router. They can scale from performance-wise 2.5 Gbps to 200 gigabit per second. They all use QFP, Cisco Quantum Processor, as the data path forwarding engine. So the QFP will process all the data paths, make packet forwarding decision, and processing all the features. So that is very important because that consistent ASIC implementation across the product family, you can expect the same feature parity, same functionality, same feature behavior across the entire portfolio. The QFP can scale up really high. It can scale up to 464,000 queues, for example. That is the type of scale required for the service provider deployment. We want to build a system with the best-in-class availability. So we build a system with a separate control plane and a separate forwarding plane. In our modular chassis, where you have a redundant route processor and a redundant forwarding engine, in the event of the route processor, the RP fail over, the forwarding engine continues data path packet forwarding. There is zero packet loss. We not only support stateful inter-chassis redundancy, but also we support stateful inter-chassis redundancy. So you can have a toolbox, and between toolbox, they will synchronize the application state, like a NAT or zone-based firewall. I would say the key unique differentiator on ASR1K is the instant service on delivery, is on the services. Because the way the QFP is designed is programmable in C. So we can directly code layer 4 to 7 services in iOS and use QFP to accelerate that service performance. So when you need to roll out new services on your existing networks, you don't need a new hardware. There's no truck roll. Very easy to consume. You just turn on the services with CLI, with netconf, with automation. Before we talk about the system architecture, let's have a brief overview the ASR1K applications in enterprise space, then in service provider space. This is what we call the pin, the place in the network. Let's walk from left to the right. Okay, if you look at the left, the ASR1K is your high-speed CPE. This is in your high-end branch or large campus where you need a 10 gig circuit connection to the WAN. This is where the ASR1001X, ASR1002X are very popular deployed. ASR1000 is the SDA border node. How many of you are familiar with Cisco SDA architecture? So SDA is the Cisco software-defined access architecture for campus, for branch, fabric, controlled with DNA automation and the policies. So in the SDA framework, you have the network edge node, which connecting to the network endpoint. Then you have the border node, which extending the SDA fabric to the external domain, like a WAN, like your data center. So ASR1000 is positioned as the SDA border node. WAN aggregation, this is where ASR1000 play a predominant role. We support pretty much all the WAN aggregation technology under the sun. MPLS VPN, Layer 2 VPN, Layer 3 VPN, and the IPsec VPN, including DM VPN, dynamic multi-point VPN, to give you the hub and spoke type of network topology, Flex VPN for remote access, and the GET VPN, group encrypted VPN, give you the encryption for your overlay networks, like your MPLS VPN. And of course, now ASR1K is integrated into the SD-WAN architecture. So ASR1K can be managed by the vManage, join the SD-WAN fabric. We'll talk about that later. ASR1K is the DCI. Now moving to the top right, ASR1K is your data center interconnect platforms. So you can use ASR1K to build a layer 2 extension between your data center using like Ethernet over MPLS, VPLS, virtual private LAN services, or OTV, overlay transport virtualization to build layer 2 extension. And the ASR1K also support the EVPN VXLAN Layer 3 gateway. So you can have an ASR1K to pair up with your Nexus 9K in the data center to learn all the tenant route through MPBGP and to terminate the VXLAN tunnel in the VTAB, then hand off the traffic to the WAN using MPLS VPN. ASR1K is a very popular internet gateway, a highly scalable internet gateway. You can have 3, 4, 5 different ISP peerings with service provider to download the full internet routing table for both IPv4 and IPv6. On top of that, you can add in services like network address translation, zone-based firewall, AVC, application visibility control, which will give you the visibility to see what applications are actually consuming your internet circuit. Cloud Edge. What we mean by that is the ASR1K can be used to extending your WAN circuit all the way to the cloud. We're going to talk about one of that use case later as well. In the service provider space, the CPE, similar use case as the enterprise, just now this box is managed by the service provider. In the edge, ASR1K is a provider PE platform. Very scalable, very popular, widely deployed PE platforms. It can scale up to 8,000 VRFs, 8,000 BGP sessions, and millions of routes. BNG, Broadband Network Gateway. So ASR1K can be used to terminate your broadband subscribers from residential as well as from the business subscribers into the ASR1K. IWAG, Intelligent Wireless Access Gateway, provide Wi-Fi offload options to 3G and 4G mobile providers. Now moving to the top right, ASR1K is a CGN platform, carrier-grade net platform. We support a variety of CGN technology, Net 4.4 translation, Net 6.4 translation. Net 6.6 is also called NPTv6, IPv6 to IPv6 network prefix translation. We can scale up to 24 million sessions. ASR1K is an ISP peering platform. It is also an LNS, L2TP network server, which is a broadband aggregation in the wholesale model where the wholesale provider encapsulates the PPP session in the L2TP tunnel, ship the tunnel to the service provider space, terminate the session on LNS. And ASR1K is a route reflector, very scalable route reflector. It's probably the most widely deployed route reflector in the industry. It's about 24 million routes with 4,000 route reflector clients. Now let's talk about the system architecture. So again, stop me anytime if you have questions, okay? For the folks, if you're tired and if you want to take a nap, please give me 3 minutes of your time, okay? Because this is the single most important slide. In this slide, you're going to have a fundamental understanding how the ASR1K system put together, how it works, and how the packet flow. Many slides we talk about later on can refer back to this slide, okay? So follow me this here. So ASR1K has 3 basic building blocks. The route processor, manage the system, handle the control plane. What is really special about ASR1K is the ESP, Embedded Service Processor. This is your forwarding engine, forwarding processor. This is where the QFP reside in. QFP have 2 subsystems. The PPE is the packet processor engine. It's a multi-core, multi-thread processor. Each thread is able to independently run the feature to completion. BQS is the traffic manager. This is the component to scheduling the packet out of your system based on your HQAS, hierarchical QoS configuration. It also has a crypto coprocessor, we call it crypto ASIC. It's used to accelerate your IPsec performance, so dedicated for IPsec encryption and decryption. The third component is the carrier card and the interface. We have SIP, SPI interface processor, Ethernet LAN card, which has a built-in gig and 10 gig interface. And the newer one is the MIP, modular interface processor. It carries the Ethernet port adapter. The key takeaway here is that regardless what type of LAN card you have it, it's either the modular or same for the fixed chassis, those built-in I/O interface. They do not participate in the packet forwarding decision. Okay, they don't have that intelligence, just dummy I/O interface. They just have a preliminary packet buffering capabilities. So when the packet is coming in from any of the I/O interface, the LAN card will perform a common classification. So for example, the packet with IP precedence 6 and 7 will be classified into the high priority queues in the ingress buffer, and 0 to 5 will be classified into the low priority queues in the ingress buffer. Then the LAN card will first send the high priority traffic up to the active ESP before serving the low priority queue traffic. So by design, the system will honor the packet marking from the ingress. And if you don't like that classification, if you say, I don't trust any ingress marking, I want every packet coming in into the class default, you can do so. There's a command on the interface LAN card. You can change every packet from 0 to 7, go to the low priority queues. So once the packet gets shipped up to the forwarding engine, the QFP will assign the packet to one of the threads. And that thread will run the feature to completion, do all the ingress features, make a packet forwarding decision, do a fib lookup, find the next hop, then process all the egress features. And the BQS will scheduling the packet out of the system based on your MQC configuration. If you apply the IPsec feature on that packet, then the QFP will send the packet to crypto ASIC to do the IPsec encryption and decryption. If the packet it is sent to the router itself as a control message, let's say a BGP update, the QFP will pump the packet to the control CPU. And if the router itself want to send a routing update to its peer, the RP will inject the packet back to the QFP. So you'll see that without a working ESP, you cannot send a single packet in or out of the system. So that makes ASR1K a centralized forwarding architecture. Very important concept. Every LAN card, they have redundant ESI, enhanced SerDes interface connection to both active and standby ESP. You see we have two ESP, active, standby. So what happened is the route processor, the active route processor, always synchronize the fib state to both active and standby ESP. So both ESP always have identical copy of the fib. So that in the event of the active ESP failed, the carrier card will immediately switch over the packet to the standby ESP because it has redundant ESI, the SerDes interface. And the standby ESP is immediately able to forwarding the packet. So that is how we can achieve less than 50 millisecond packet loss when you have the ESP switch over. You may also notice that every building block have a CPU, right? There's a CPU on RP. There's FECP, forwarding engine control CPU, on the ESP, which manage the forwarding engine, manage the board, and program the QFP and the crypto ASIC. Then there's IOCP, IO control CPU on the LAN card, which load the interface driver. So that gives us a distributed control plane architecture. And this modularity allows us to gracefully upgrade each of the components during the in-service software upgrade to minimize the downtime when you upgrade the system from image A to image B. The fixed chassis have the same architecture, have the same 3 building blocks as the modular chassis. Okay, the only thing difference is that it doesn't have the redundant RP and ESP, and it has a single CPU. It has a single CPU to manage both RP subsystems, the ESP subsystems, and the line card, the I/O subsystems. Otherwise, the same packet flow, the same centralized forwarding architecture, the same distributed control architecture. Any questions? So we talk about the modular chassis first, then we talk about the fixed chassis. Okay, so this table gives you the overview of the modular chassis. We're going to focus on the X chassis. Okay, we're going to focus on what's really new. So the X chassis brings 2 new innovations to the product. First, we upgrade the mid-plane bandwidth to 200 gigabit per second. The existing chassis, the mid-plane bandwidth is a 40 gigabit per second. So the X chassis allows us to support 100 gig interface, 40 gig interface, and a high-density 10 gig interface. Secondarily, we redesigned our power supply systems. We're using this modular power supply unit. We call it PSU. You can have up to 6 of them. They're highly efficient, able to do load sharing among themselves. Each of the PSU is hot swappable. Each PSU is rated at 1100 watt AC or 950 watt DC. So they can provide sufficient power into each of the slots to power up next generation route processor, next generation forwarding engine, and the next generation line card. So it is a future-proof chassis. And the slot on top of the PSU is the slot for route processor. It supports RP2 and RP3. Then 1 level up, this is the slot for the ESP, the forwarding engine. The 2 slots on the very top are the redundant RP and ESP. The 3 slots in the middle are the line card. You can have any of the line card we talk about in any one of the I/O slots. The 1006X has 2 differences compared to 1009X. First, it has 2 I/O slots instead of 3. Okay, so 1009X has a 3 I/O slot. 1006X has a 2 I/O slot. Secondarily, the 1006X it does not support ESP200. So on the forwarding engine, it does not support ESP200. But it will able to support the future generation ESP with the ESP200X. Oops, did I just leak the information about the next generation ESP? So please don't tweet me, I'll put my code on the Facebook, okay? I don't want to become the Cisco leakers. So this table gives you the compatibility matrix, what module is supported in which chassis. Pretty straightforward to read, okay? So let me know if you have questions. The line card, we're going to talk about the MIP, which is the newer one. The MIP 100, this line card have 100 gig full duplex ESI, the SerDes interface, connection to the mid-plane, which connecting to both active and standby ESP. And you can have 2 of those 1 by 100 gig EPA, the Ethernet port adapter, in 1 carrier card. So this line card is designed to support a 2-to-1 over subscription. We support 6 types of EPA, 18 by 1 gig, 10 by 10 gig, the 2 by 40 and the 1 by 100 with the CPAC optics, then 2 by 40 and the 1 by 100 gig with the QSFP optics. So 2 messages here. First, those EPA is not only supported on the modular chassis, but also supported on the 1002X, the fixed chassis, which we're going to talk about the next. Second, you see that except the two EPA in the middle, the rest of the EPA all support MACsec encryption. So they allow you to do layer 2 encryption at a LAN rate across Ethernet transport services. Remember in the building block slide, I said all the data paths features are processed by the ESP, right? So either the QFP or the crypto ASIC doing the encryption for IPsec. Well, the MACsec is one exception because MACsec is an Ethernet encryption. It directly processed on the PHY chip on that interface. So that is how you can reach a LAN rate performance without performance penalty to your every other services. So you can turn on MACsec on that port, give you LAN rate performance without impacting to the system overall performance. The raw processor, RP3 is the newer one. Okay, it's the new generation raw processor. It runs an Intel Broadwell quad-core processor clocked at 2.2 gigahertz. The DDR4 memory can scale from 8 gigabytes to 64 gigabytes. This combination, the Intel Broadwell and the DDR4 memory, give you a system 30% more faster compared to RP2 when it comes to the control plane convergence time, okay? So if you run BGP, you run OSPF, you're going to find out RP3 convergence at least 30% more faster if you're running RP2 in the current network. And represent a 60% more scalable for the control plane. For example, the RP2 support 6,000 DMEP in spoke sites. RP3, it can scale to 10,000 DMEP in spoke sites. And the route scale is almost doubled. RP2 support 4 million routes. RP3 support 8 million routes. Let's talk about the ESP. So this is the heart of the system, right? This is what pumping the packet blood throughout the systems. This is where the QFP reside in. Again, centralized forwarding paradigm, all programmable, a multiprocessor system based on QFP. We're going to talk about a QFP next. What the second thing the ESP has is the traffic manager, the buffer queuing scheduling system. It does your MQC configuration, the traffic shaping, the queuing, and the scheduling. It's all done in hardware. You can configure as many queues as you want. You will not see performance degradation as you would see in some of the other platforms. The traffic manager, the BQS, support very high level of scheduling. It can actually support a 5-level HQAS scheduling, so more than what your MQC configuration allow you to do, which you can only do 3-level, right? You do a parent and grandparent and child, so 3-level. Where on the traffic manager, the BQS, allow you actually able to do 5-level HQAS scheduling. And the priority queue propagation is supported throughout the schedules, throughout the QS scheduling systems. So you configure the priority queue once, and that priority will be propagated throughout your scheduling systems. So the high priority queue always get ahead, never blocked by the low priority traffic. So that's how we can guarantee the low latency traffic for your voice applications. Another component on the ESP is the crypto coprocessor. We want to provide a scalable security solution on the box. So we have this crypto coprocessor dedicated for all the IPsec encryption and decryption. That allow us to provide a very high scale, high performance IPsec for the ASR 1000. It also contains all the ESI link. So ESI link will hook up all the carrier card, aggregating traffic up, then send traffic back down. This is the #1 FAQ on the ASR 1000. A customer always asks me, hey, Jason, when you say ESP100, you said it's 100 gig. Is that 100 gig full duplex or is it 100 gig half duplex? So I made those, for example, for illustration purpose. Okay, if you look at the top left example, you have 50 gig of east-west unicast traffic and 50 gig of west to east unicast traffic. So in total, in aggregately, you're asking the ESP to process 100 gig of traffic. This is what the 100 gig means. So the aggregated traffic, the amount of traffic the ESP able to process and send out. And if you look at the bottom right example, you have a 10 gig of a multicast stream coming into the system. You have a 10 receiver waiting on the other side, right? So you're asking the ESP to replicate the packet 10 times, sending out as 100 gig. You also have a 20 gig of east-west unicast traffic. So in total, you're asking the ESP100 to process 120 gig of traffic. So you're oversubscribing the system. This is where the traffic will be dropped, and the drop will be based on your MQC configuration. Let's talk about the QFP itself, okay? QFP is a custom-designed network processor designed at Cisco. It is based on the genealogy of Metro NPU, the Metro network processor used in the Cisco CRS-1 systems. The architect who designed the Metro learned what he did in the CRS-1. He basically wanted to do something more than just layer 3 processing. So it took about 5 years to design from Metro to QFP to make it scalable to support layer 4 to 7 services. The architecture itself can scale more than 100 gigabit per second. We're still continuing to evolve it. It is a multi-processor systems, so 64 multi-thread cores, 4 threads per core, make it look like there are 256 processes to simultaneously processing the packet. It got great packet replication capabilities. It can replicate packets so fast, almost exponentially. So that allows us to provide very high-scale multicast services. There are a lot of stock exchange around the globe are using ASR1K to multicast the stock information to the brokers, to the traders, to those trading floors, to the brokers. Those QFP can be matched in 1, 2, or 4 together to be cascaded to provide higher ESP throughput. For example, the ESP100 is a mesh of 2 QFPs, and the ESP200 is a mesh of 4 QFPs. Any question on the modular chassis? Let's talk about the fixed chassis, okay? We are going to focus on the HX chassis, which is a really new one. First thing first, the HX is not meant to replace the X chassis. If you look at this line, the throughput, you see that they operate at a totally different bandwidth spectrum. The 1X and the 2X are the 2.5G to 36 Gbps platform. They're your high-end branch or your smaller one aggregation platforms. Where the HX, they're 60 gig, 100 gig systems. So they really bring down that big ESP100 into smaller form factor to allow you to install them in the rack space sensitive place like a co-location facility. The 1001HX, let's start with the I/O interface. 8 built-in gigi port, 8 built-in 10 gigi port. Each interface supports a multi-point MACsec. So on every interface you can turn on MACsec. You got line rate performance for layer 2 encryption. The control plane is an Intel Ivy Bridge, a quad-core CPU clocked at 2.5 gigahertz, a DDR3 memory, default 8 gigabyte, upgradable to 16 gigabyte. The forwarding plan is a single QFP capable of 60 gigabit per second forwarding capacity. The license model on the ASR 1001HX is a pay-as-you-grow based on the built-in port. So by default, you will get 4 10 gig and 4 gig interface. They're enabled by default. The additional port can be licensed in pair. So if I need to enable the 5th 10 gig port, I would buy a pair of 10 gig license. The crypto module on the 1HX is field upgradable. So you can order the system without the crypto module. But some point of later on in your deployment cycle, you said, OK, I decide I need to enable IPsec. So you can order that module separately, power down the system, open up the top cover, align the module with the motherboard, and the full school, you can tie in the systems, then power the system back up. The crypto module comes with a bandwidth license of 8 gigabit per second default, upgradable to 16 gigabit per second. The throughput license is benchmarked in IMIX, so internet mixed traffic, which is average about 362 bytes. What that means is once you upgrade to the top tier license, you actually unlock the crypto module performance where you can actually reach 29 gigabit per second with large packet size, 1,400 bytes. ASR 1002HX. 8 built-in gig port, 8 built-in 10 gig port. Again, each port supports MACsec encryption. In addition, it has the EPA slot. So this, yes, question.
You said MACsec is processed on the ports. Do I need a crypto module to do MACsec?
Very good question. So the question was, you said the MACsec is supported on the port, so do I need a crypto module for the MACsec encryption? The answer is no. The crypto module is only used for IPsec. For MACsec, you don't need this crypto module. Yes, question.
So the capacity of the module, for example, this one, 100 gigs, is that line rate, or is it simulated at some packet size?
Which module you're talking about?
ESP 140. Performance numbers you're giving, are they at a certain packet size, or is it just line rate?
So good question. So the question was the ESP100, when we say the 100 gig, is the line rate at what packet size, or doesn't really matter, right? So the answer is, in our performance benchmark, the performance is always benchmarked at IMIX, so internet mixed traffic, which is, again, 362 bytes. And with smaller packet size, you will not going to reach 100 gig, but with larger packet size, you're definitely able to do more than 100 gig. I mean, the actual safe performance for the ESP100 is about 125, 126 gig. We just round it to call it 100 gig.
Can you find the packets per second performance numbers somewhere?
So the question is, can you define the packet performance number? You're asking the median packet per second, right?
No, just the performance numbers available online for packets per second.
Yeah, so the question is the performance number available online. I believe in our CCO data sheet, we did document the median packet per second. So if you Google ASR 1000 ESP data sheet, we have a table for each of the ESP and the fixed chassis. That's where you're able to find the packet performance. Any other questions? Okay. So the 1002HX, we also have a NIM module. The NIM module is the same NIM module as your ISR 4000, but the only NIM module we supported on this chassis is the SSD drive. It's really for storage purpose. The same control plan as 1HX, but with a bigger memory. 16 gigabyte default, upgradable to 32 gigabytes. The forwarding engine, the QFP, is a mesh of 2 QFP together to provide an aggregate of 100 gig forwarding capacity. The same license model based on the built-in port. okay? This EPA module does not require a license. So the license only apply on the built-in I/O interface. The crypto module is also field upgradable. It's located on the side of the chassis. So again, default 8 gigabit per second crypto performance, upgradable to 16 and 25 gig. So once you upgrade to top tier crypto license, you are able to reach 39 gigabit per second with IMIX traffic. With the 1400 byte packet, with large packet size. Any questions on the hardware architecture? Yes?
In terms of the optic, can I use SFP plus duck cables to connect the...
The question is, can I use SFP plus duck fiber?
Yeah.
Yes, absolutely, yes. Any other questions? All right, let's talk about the software architecture. The ASR 1000 is running iOS XE operating systems. I mean, this shouldn't be new to you, right? The iOS XE operating system is optimized for the enterprise networking. It's available on your ASR 1000, on the ISR 4000, ISR 1000, the Catalyst 9000 switch, the wireless LAN controller. So the iOS XE is a modular operating system built in the Linux. What we did is we took the lot of operating system responsibility out of the iOS process. Now the iOS process just focused on your control plane running. So for example, we took off the responsibility of managing the chassis out of the system, running them as a separate process called a chassis manager. Then we also have this forwarding manager, which acting as a platform adaptation layer. I mean, the iOS doesn't understand the QFP. They don't talk to each other. So we have this forwarding manager as an adaptation layer, able to communicate iOS FIB to the route processor, download to the forwarding engine, and program the QFP. By the way, you'll see there's no forwarding manager on the LAN card. Just to prove the point, we said at the beginning that the LAN card doesn't have any forwarding intelligence. We upgrade the entire OS to 64-bit. That allows us to support much higher addressable memory. Okay? That's why you see we able to scale from 8 gigabyte to 64 gigabyte memory and scale the route up to 8 million. We talk about those high availability innovations, right? We said in the event of the route processor failover, because that separation of a control plane and a forwarding plane, ESP will continue the packet forwarding. There's 0 packet loss. When the ESP failover, because RP synchronized the FIB state to both active standby ESP, and the LAN card has redundant ESI link to both ESP, so we can achieve less than 50 millisecond packet loss. One of the innovation ASR 1000 did was the software redundancy. So in the fixed chassis, right, we said on the fixed chassis, there's a single RP to manage all the 3 subsystems, RP, ESP, IO subsystems. What we did is we allow you to spin off 2 iOS process in active standby. They will synchronize the control plane state. So in the event of the iOS crash, the standby process become active while you have your QFP will continue the data path packet forwarding. So let's take a look at each of the process, what they do, okay? So the chassis manager responsible to initialize the card, initialize all the process on the route processor, and manage, detect the LAN card OIR event, and monitor the environment and the power consumptions. Then you have the iOS. That's where you generate the CLI config. set up your routing adjacency, set up the RIB, compute the FIB. Then the FIB get downloaded to the forwarding manager on the RP, we call the fman RP, which synchronize the FIB state to both active standby ESP, then they get pushed down to the forwarding manager process on the ESP, which in turn use that information to program the QFP client and driver in a very indense copy of the FIB. So when QFP forwarding the packet, it will do a FIB lookup on that QFP resource DRAM, able to very fast make a packet forwarding decision. It also does all the statistics collection. So when you do show policy map interface blah on your iOS CLI, you see the number of packet and the byte from your class map, from your policy map. Those stats are coming from the QFP client driver. What's really unique on the carrier card is just the interface driver. The fixed chassis. The fixed chassis has the same software architecture as the modular chassis, right? All the three subsystems we talk about, the RP, the ESP, the I/O subsystems. The only difference is there's a single control CPU, so there's a single kernel, and all the three subsystems running on top of this kernel. How many of you have joined one of the SD-WAN sessions? Awesome. I mean, if you haven't been to any SD-WAN session, you didn't come to Cisco Live, okay? So in the end of the deck, I have related sessions. That's where I give you the reference of all the architecture or technology we have been talking about today. So this is to give you an overview how the ASR 1000 is integrated into the SD-WAN fabric with the XE SD-WAN software. So if you go to CCO software download today, if you choose ASR 1000 platforms, you're able to see there's XE software, then there's also XE SD-WAN software, okay? So how did we do that, right? How did we marry the SD-WAN, the Viptela software stack together with the iOS XE operating system? We took the sidecar approach. Have you ever watching the sidecar race? Right, there's a driver on the driver's seat, give the direction where the vehicle is going. Then there's someone sitting in the side pocket, like holding positions to balance the vehicle, especially when there's a turn. So that is the sidecar approach we're taking. We're running the iOS process with the SD-WAN software stack side by side, natively on top of the Linux kernel, okay? So everything here is the same iOS architecture we talk about, right? The RP, ESP, I/O subsystems. Now we're adding the SD-WAN software stack natively on Linux kernel, running side by side with iOS. For example, when the system comes up, the Linux kernel comes up, it will initialize the iOS process as well as the system manager process. The system manager process in the Viptela software stack is the process responsible to spawn every other process and monitor those processes. And the first process is going to bring up is called the vDaemon. So for an XE SD-WAN router able to join the SD-WAN fabric, the first thing it needs to do is to set up a control tunnels to the vManage, vSmart, and vBound. And vDaemon is the process responsible to setting up that tunnels, acting as a tunnel endpoint. That tunnel is a TLS encrypted. So the vDaemon will do all the encryption and decryptions. Every other control message will go inside this tunnel, which including OMP, Overlay Management Protocols. Just think it as a BGP with different address family, subsequent address family, to able to advertise the SD-WAN overlay routes from vSmart, from the controller to the XE SD-WAN routers. As part of the update, the router is going to learn what's so-called a TLOC, transport locator. Again, if you're familiar with the BGP, so this is your BGP with extension, the OMP. Then the TTM is the extension of the BGP next hop, okay? So based on the next hop information, the TTM, the tunnel table manager, will build a full mesh tunnel with any other XE SD-WAN routers for that VPN membership you want to form for the data plan. So that is what the TTM is. There are also FPM, Forwarding Policy Manager. So as part of your vManage policy configuration, you would provision data policy, like your QoS policy, or application policy, which is you tell, for this application, I need a path with less than 150 millisecond latency, with less than 1% packet loss. So that's type of the policy you would set up for applications. Then those policies get compiled and get pushed down to the data plan through the forwarding manager RP, forwarding manager FP, then get programmed in the QFP. You see, we do a lot of re-leveraging on the existing architecture. FTM, forwarding table manager, which is, to think it as a FIP in the iOS, okay? But this FTM is used to build the forwarding table for the SD-WAN overlay networks. So the FTM will also compute the FIB and download the FIB through fman RP to fman FP, then get programmed into the QFP. So after all, QFP is still your forwarding engine for processing all the data path packet. To make that marriage to able to work, we're introducing some new process in the iOS. The first one is called OMP agent. Right, so on the SD-WAN architecture, you have this concept called the service side, which is your LAN-facing interface. It's what's facing your internal campus, okay? That's where you're running your own existing network protocols, either OSPF or BGP. Then those routes get updated through the OMP agent to the OMP, get sent up to the vSmart controller. So the rest of the SD-WAN fabric know how to reach you, okay? And SD-WAN subsystems. This process is used to synchronize some process between iOS and the SD-WAN software stack. For example, the VPN definition in the XE SD-WAN router will be based on the VRFs, right? And you have the chassis manager to bring up all the interface and realize as IDB interface database in the iOS process, then those interfaces get propagated into the SD-WAN so that SD-WAN stack know, okay, I'm going to use this interface as my underlay for the WAN transport, and the other interface is my LAN-facing interface. So the subsystems, the SD-WAN subsystem is going to synchronize the information in between. Any questions? Okay. We have a lot of innovations in the iOS XE software. One of them is the programmability. This is something I'm very passionate about, okay? Outside the ASR 1000, I'm also driving a couple other innovations. One of them is the programmability. So this gives you the programmability interface stack from the iOS XE. What we're doing is we're exposing the industry standard interface, the netconf, resconf, and the gRPC northbound, and they give you the ability of the device. And the ability of those devices are represented in the YANG data model. The data model can be open model based on industry definition of IETF or from OpenConfig forum, or they can be native model, which are iOS XE specific models. The type of model can vary from configuration model, which allow you to apply the configuration to the device, or they can be operational model, which allow you to extract information from the device. So we publish all our data model in the GitHub. okay? And the latest release we're publishing is 16.10. So those models are part of your iOS XE software, okay? When you download the software, when you're running your ASR 1000 with the 16.10 release, and all those data model capabilities are built into your software. One of the very popular use case of the programmability is telemetry. This is what the web OTT they want to do. For example, Google, they want to pull more than 200,000 OID per minute from a network management station. You know this cannot be done by SMP. The telemetry can substitute SMP and get more benefit over SMP. We know that SMP is a very CPU-intensive process. It prone to OID timeout and slow OIDs. So with shorter the polling intervals from multiple polling stations, you can easily toast the box. But with telemetry, you can do cadence in seconds, irrespective of number of receivers. Because telemetry using a push model against SMP's pull model. Think about the New York Times, right? They have millions of subscribers. But every morning, 6 o'clock a.m., all their subscribers are going to receive the newspaper in their mailbox, on their doors. Same idea for telemetry. Whenever you configure a subscription with the cadence timer, when that cadence timer expires, the device will stream out all the relevant data to the receivers. So we support the netconf dial-in model and the gRPC dial-out model. What the dial-in model means, you need to have a client setting up a netconf session to the device. And through that netconf connection, you're configuring subscription and you're receiving the publications. And the gRPC in 16.10 allow you to actually, using CLI, make a configuration for the subscription you want to receive. And the stream data are going to be streamed out to the receivers using the gRPC, the Google Remote Procedure Call interface. Both methods, they support periodical subscription. So you can receive the subscription every 10 seconds, every hour, every day, or you can receive the subscription on change. So for example, if your interface goes up and down, you're going to receive a notification through the telemetry. Any questions on the iOS XE software architecture in general? Yes?
Do the two ESPs sync multicast state?
Two ESPs sync what?
Multicast state.
Multicast state. So the question is, does two ESPs synchronize multicast state? So if you go back, if you remember the building block slide, right? I said you have the raw processor, the RP, running the control plane. So same for multicast. The RP going to build your multicast PIM neighbors and build the MFIB, the multicast FIB table. And the RP will synchronize that MFIB to both active and standby ESP. So it is RP's job to synchronize the both active standby ESP and make sure they have the same copy of the MFIB. So same goes to the ESP switchover. The ESP standby become active. It's immediately able to forwarding multicast to replication using the MFIB. Any other questions? All right, let's talk about the interesting part. I mean, this is where you can actually use your ASR 1000. And we're going to talk about a couple very new and very popular use case. Let's start with the cloud edge. We said the cloud edge is the use case that you're extending your WAN all the way to the cloud. So this is the use case to connecting your on-premises network to your Microsoft Azure cloud using ExpressRoute. Any of you using a Microsoft ExpressRoute, or you're planning to do so? So the Microsoft ExpressRoute is a dedicated high-speed connections between your on-premises network to the Microsoft Azure. So what we did with Microsoft joined together is that we developed this joint validate design document. It has a link on ccu.com. It including all the step-by-step requirement for you to set up that ExpressRoute circuit. It also including the best practice how to set up a high availability connections. The ExpressRoute using BGP as the layer 3 connections. So between your Cloud Edge, which is ASR1K, and the Microsoft Cloud Edge platforms, it will set up BGP sessions to exchange route. And that connection is set up by the connectivity providers, typically like in a co-location facility, like Equinix. And there are a lot of providers in Europe, I know like a BT, Orange, they also set up that ExpressRoute connections for you. So in that joint validate design, we have the best practice, how to use BGP AS paths, how to use the local preference, how to use the BGP communities to optimize the routing for you. It also including the network address translation configuration best practice. When your on-premises network is running private IP space, you need connecting to the Office 365, which is the public cloud. The Microsoft is going to require you to do netting on your Cloud Edge device. It also including the network security best practice. Typically, this connection to the Azure, which is your private cloud, is your trusted networks. But this connection to your Office 365, which is a public cloud, require you have, for example, DMZ or firewall connecting from the Cloud Edge, connecting to your networks. We have all that documented in the validate design. And you also have the ability to set up IPsec tunnels from the Cloud Edge all the way to your VPC gateway in Microsoft Azure. We also support Cisco solution support. What we mean by that is the Cisco tech engineer will support end-to-end Microsoft ExpressRoute connection for you. So what we did is we have the Microsoft engineers, their architect, trained Cisco tech engineers, how the ExpressRoute works, what are the common problems they're seeing, what are the troubleshooting steps. So now Cisco tech engineers is the expert of the ExpressRoute, and they can troubleshoot end-to-end problems for you. So we own that solutions. Encrypted traffic analytics, ETA. I don't know if you have chance to go to the World of Solution. There's a NOC booth that show you the operation of the Cisco Live from Cisco IT. One of the big screens you see there is a stealth watch, right? What that screen show you is all the malicious activity being detected and being mitigated right here in Cisco Live. So how did we do that? The ETA give you the ability to find malicious activity hidden in the encrypted traffic without decrypting it. It can do so by using enhanced NetFlow. So we're including some special attribute in the NetFlow record, which including the initial data packet, we call it IDB. That initial transaction between the host and the server on the internet, which is stealing the information from you, they have the initial handshake. And that handshake including very important information for us to identify those type of packet. It also contains including information like the sequence or the length of the packet and the timing of those packets. Those patterns, those behavior of the packet able to help us to identify those threads. So now you have enabled the ASR 1000 as a sensor, a security sensor in your network. They're able to export the information to the Cisco Stealth Watch. In the Cisco Stealth Watch software, we implement the enhanced analytics and the machine learning capabilities. So they're able to identify the thread and report the thread using metadata to the Cisco Cognitive Cloud. So Cisco has a Talos research lab. And in that lab, they run a global threat map. So basically, it's a who is who on the internet, the dark side. So they are aware of all the malware campaign running on the internet. And from the metadata they received, they're able to correlate your specific event to what's going on the internet. And they're able to identify and give you the assurance that you are indeed being compromised. Or maybe it's not, but they give you that certainty. And so you can take actions to mitigate that threat, to quarantine that compromised host. Another use case of the ETA is for compliance. For the retail industry, they require you have a PCI compliance. So all the POS machine, the POS terminal, the point of sales terminal, they require you, for example, run TLS 1.2 and above, right? So you can use ETA to run an auditing of an internal network crypto compliance to see all the applications running between your client and the servers if they are PCI compliant. So the deployment model for the ETA on the ASR 1000 is on the one aggregation. So the traffic coming from the branch aggregated by the ASR 1K in the headquarters, you enable the ETA, that net flow, the enhanced net flow on the connection to your data center. So you can capture all the client-server communication within your organization. And you can enable ETA on your ASR 1000 when they're acting as an internet edge. So before those traffic send out to the internet host, they're stealing information from you, we're able to censor all those activities. So we have this CVD published on the Cisco.com, the different deployment scenario for ETA and the type of configuration required. And we have this third-party Mircom report that did a study how quickly the ETA can detect the malicious activity in the number of hours instead of weeks or even months. Segment routing. How many of you have heard of segment routing, or you may already deployed the segment routing? That's great. Segment routing really simplifies your WAN transport. It does so by take a different approach. It is using a source routing paradigm by encoding the path in the packet header as order list of a segment. In another word, MPLS label stack. So that you can remove the control plane protocol like LDP, the label distribution protocol. You don't need LDP to distribute your labels. And you don't need RSVP-TE to signaling the label for your traffic engineering. We can simply do so by augmenting, by extending your IGP, either OSPF or ISIs, with a segment routing extension to distribute the labels. So we simplify the label stack, and we simplify the control plane, and we avoid many problems which currently presented in the MPLS networks. For example, your LDP and IDP synchronization. Sometimes your IDP may already converge, but your LDP is not converged. So you're actually sending the packet to the black hole without the proper label stack, so on and so forth. By doing so, because we're using IDP, we natively supporting ECMP, so segment routing natively supporting equal cost load balancing. It also supports we call the topology independent loop-free alternate, which in other words is fast readout. But without your configuring of RSVP-TE backup paths, the OSPF and ISS extension with segment routing natively support to build a post-convergence path. For any link failure, node failure, the segment routing able to automatically reroute the packet to the alternate path, to the post-convergence path. Actually, this is one of the top use cases I've seen the customer deploy the segment routing. Because we're using the label stack as a forwarding plan, so all your existing VPN services, layer 2, layer 3 VPN services, still run as this is on top of the segment routing transport. So if you look at this topology here, we have two types of segment identifier. You have this node segment ID, which is a global unique identifier. It's like your loopback address, right? So you assign a node SID of a 16006 to PE2. Then every network node in the segment routing domain sees 16002, it knows I just follow my IGP path, send the packet to PE2. A second type of segment identifier is called adjacency SID. This is a local unique, local significant identifier automatically generated for the IGP adjacency for that link. So N going to tell B that, hey, if you want to send traffic to me using this link, you're using my adjacency SID. So now you can imagine with a combination of a node SID and adjacency SID, I can send a packet through any node, any link in my network. That's very powerful, right? So in this Cisco validated profile, again on cisco.com, we publish the top 5 popular use case of a segment routing. Each use case including the description of that use case, why you want to do that, the topology for that use case, the feature required for that use case, and the scalability we validate for you, and the configuration as well. Okay? So we won't have time to walk through each of those use cases, but they're available on cisco.com. Also in the reference section, I have my own segment routing breakout session. So you can also watching that recording and the presentation for segment routing as well. I have one breakout session for segment routing use case for the enterprise. Ethernet VPN. Ethernet VPN is the next generation multi-point VPN technology. It uses multi-protocol BGP in the core to exchange and advertise MAC address, just like exactly the way you do today for your layer 3 VPN, right? You run MPBGP to advertise your VPN v4, VPN v6, multicast VPN prefix. Now you can use MPBGP to advertise the MAC address between the PEs. Well, it's still using the data path learning on the data path MAC address learning on the access-facing interface. So by doing so, you're able to leverage all your operational expertise and the design principles that you already have for the layer 3 VPN and apply that to the Ethernet VPN services. And this architecture able to overcome a lot of shortcomings coming from VPLS, virtual private LAN services. It allows you to build all-active, multi-homing, per-flow load balancing connections from your CE on the site, dual homing to both PEs. So if you look at the couple scenarios we have there, on the right, you have the CE3, it's a single home to PE4. Then on the CE1, on this side, you have dual home CE1 to PE1 and PE2, but with one active link, the other is standby. Well, on the CE4, you can have dual homing to both PE2 and PE3 with both link active. This is the most common deployment scenario I have seen. And Ethernet VPN also provide very rich services. So what you can do is you can configure this port-based service instance. This is between your P and the CE. On the CE-facing side, you can configure port-based service instance. So what you can do is you can have group the entire port, how many VLAN on that port, all the VLAN will connecting to the EFP, the Ethernet flow point, which connecting to this bridge domain, which associated with the EVI instance, Ethernet virtual instance. So the Ethernet virtual instance is your VRF table, but in the layer 2, okay? So it's your VRF, but carry the MAC address. Then you can have the VLAN bundle services. So in this services, you group number of VLAN together, you mapping that to a EFP, the Ethernet flow point, then connecting to one bridge domain, then associating that bridge domain with the EVI instance. In the third use case, you have the VLAN-based services instance, so it's simple one. One VLAN mapped to one EFP, mapped to one bridge domain, mapped to one EVI. The last use case is called the VLAN-aware bundle services. So you can have the different VLAN mapped to their EFP, but mapped to bridge domain, but then you aggregate multiple bridge domain together into single EVI. I mean, this is typically used by the service provider because they have a limited number of EVI instances they can provide, so they want to do aggregation for you, and basically one EVI per customers. There are three components to make the EVI feature to work. The first one we said is the EVI, right? To make the EVPN to work. The first component called EVI, EVPN instance. We said this is your VRF table, but holding the MAC address, okay? The second one is called Ethernet segment. So how we're doing the multi-homing, we need some sort of identifier to identify your site, right? So the Ethernet segment, the ES, will represent a site to connecting one or more PEs, okay? So because of the ES, the Ethernet segment ID, it can make sure the packet goes out from that same site, doesn't loop back to the same site, okay? The third component is the BGP, right? So we developed a number of new BGP address family, sub-address family, and the BGP communities to carry different type of route, different type of community with extension, so that they can use to advertise the MAC address, withdraw the MAC address, to handling the split horizon scenarios, and handling aliasing. Aliasing is multiple exit point. How do I do load sharing, load balancing? So this is what the Ethernet VPN is about. Any questions? XE SD-WAN. So ASR 1000 now is fully integrated into the SD-WAN fabric. So you can have your vManage, which is a single UI for the entire SD-WAN fabric, and the vBound, which is the orchestration component of your SD-WAN fabric. It does the initial authentication of the certificate and the serial numbers from your SD-WAN routers. Then you have the vSmart. vSmart is the one we said distributing the OMP, your overlay management protocol, distributing the routing information for the fabric, right? And now you have the ASR 1000 can join as the XE SD-WAN routers. You can deploy them in the colo, in the branch, in the campus, in the data center. They share a unified data plan. And the routers are supporting the XE SD-WAN architecture are all the fixed router, right? The ASR 1000 1X, ASR 1000 2X, the 1HX, and the 2HX. At this moment, the modular chassis does not support the SD-WAN architecture yet, okay? So here I took a snapshot of from my lab when I onboarding the ASR 1001HX into my SD-WAN lab, and you can see that you're able to use vManage to manage this device where I have 3 different circuits, a Metro Ethernet circuit, MPLS circuit, and a public internet circuit. Those are my 3 transport links, and I'm able to send traffic across those links for my overlay tunnels. And you can use the vManage to manage the latency, monitor the latency and jitters of your SD-WAN fabric. Any questions for the application solution use case? So today we talk about 3 topics, right? We talk about the hardware architecture, the software architecture, how we did the integration with XE-SD-WAN. Then we talk about a couple very popular and the new applications and solutions. And you guys ask a lot of good questions. So what I really hope you can take away from this session is that it's good you understand the ASR 1000 system, how it is put together. But I really hope what you can take away back home is now you see the application space. You see the ASR 1K is really your Swiss Army knife, can solve your tough network problems. If you remember the pin, the place in the network slide we talked about at the beginning, it's almost usable in every application in some degree, in enterprise, in service provider, from the branch to the WAN, to the data center, to the cloud. It's able to reduce your network edge complexity by integrating a lot of the layer 4 to 7 services in the ASR, in the QFP. That is the main driver for us to build the box, right? You don't need many different appliances in the network to do the net, to do the firewall, to do the AVC, to do the security, and you can collapsing all that into an ASR 1000. So the ASR 1000 is very well positioned in both enterprise and the service provider. We talk about the different solutions in enterprise with XE-SD-WAN. We talk about the different use case we have in service provider, the segment routing, the Ethernet VPN, so on and so forth. So the ASR 1000 is fully embedded into the Cisco digital network architecture. It's part of the SD-WAN fabric, can be managed by the vManage. It has the entire automation and the programmability framework coming from the iOS XE. So ASR 1000 is fully embedded into the overall Cisco digital network architecture. Any questions? Well, I just give you 7 minutes back so you can rush into the cafeteria and have your meal. Thanks for coming. I appreciate it.